The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
First, I want to thank all of you for being here. Thank you, Committee 444, for putting this on. And so today I'm going to be stretching the definition of a structure. Most of the time we don't think of pavements as structures, but even though they're not classically thought as structures, I do structural engineering and I monitor pavements. So I just like to think of it as a structure on the ground. We've done a lot of work at O'Hare. I've done some long-term monitoring, and then I've also done some short-term monitoring over the long term, and I'll explain what I mean by that. And then I'll conclude with some lessons learned about this set of projects. Our partner is the O'Hare Modernization Program, so I don't know how many of you fly through O'Hare pretty regularly. I live in the area, so I'm there very frequently. And so O'Hare is going through a massive reconstruction. So this was the old layout here on the left, and they're going to this parallel runway configuration over here on the right, and it's billions of dollars. And so while I was at University of Illinois, my advisor said, hey, why don't we partner together? We'll come and do some instrumentation for you. We'll help you solve your problems if you will also let us try out some things. And so this partnership has been really, really interesting, where we've gotten to solve some interesting problems and we've gotten them to try a couple new technologies. The first phase of the project with long-term monitoring, the purpose of it is based on some test results found at the NAPTF, which is the facility run by the FAA where they do full-scale pavement testing using an aircraft loading device where they can configure the landing gears in any configuration they want and then apply huge loads. And so the first couple of tests, they started doing the loading and they found some really interesting results where all the corners of all the slab panels were cracking off. And they didn't really understand this, and they concluded that it was actually these slabs in the dry interior environment of the lab where the slabs were actually starting to curl upwards like you see in this configuration, and then they would crack off due to tensile stresses at the top. And so O'Hare said, well, we're kind of interested in that. We don't like replacing our pavements. Airport pavements, especially at a major airport like O'Hare, cause huge delays. They cost a lot of money, and they're not easy to do. Most of the pavements we're looking at are 18 inches thick or more. And so they wanted us to come and do some monitoring. We wanted to do some analytical modeling to understand this phenomenon a little bit better, and this was how the partnership was born. With the first phase, what we wanted to understand is, well, how much vertical movement are we getting in our pavement between what the pavement is sitting on and the pavement itself? And so the first thing we developed is, we call this our slab liftoff sensor, but all it is a LVDT that we've turned up on end, that we affix the core to a steel plate here on the bottom, and then the rest of the LVDT is positioned vertically. That steel plate is affixed to the base because a lot of the base under the concrete will be things like asphalt or cement treated permeable base, lots of different variations. And so we affix the base of the LVDT to under the slab, and then that way, as soon as the slab starts to lift off in the corners, we can actually measure that. This is kind of counterintuitive. You don't think of a slab actually lifting itself off, but we have measurements to show you otherwise. And since this curling effect of slabs is largely due to environmental effects, temperature gradients and relative humidity gradients, we wanted to know, well, what's the internal environment of concrete in service over the course of a year? And so the first installation we did is on this taxiway tie-in. This is on the southwest corner of the airfield, and that's the picture of the actual location. With this is part of the 10 left, 28 right runway extension on the south side. And this tie-in is 17-inch slab, and then it has 12 inches of asphalt underneath, and then it goes about 3 feet of prepared subgrade under that. So it's a really substantial structure. With this tie-in, we were allowed to actually put our data loggers right next to it. They didn't give us height requirements. Airports are pretty strict about that. But the problem is, they said, well, the only power we have in that area is 440 volt, 3-phase that they use for the landing lights. Our data logger can't handle that, and so we had to get a little bit creative with that. For the installation, as I said, we installed several of these lift-off sensors where you can see here it's positioned vertically. Because this tie-in, if you look at this map, doesn't really go anywhere at the moment. This is actually a very recent Google Maps image. They actually allowed us to mount our sensors on the surface as well. We wanted to know, well, how much are these cracks opening and closing, and we like data, so we also included some LVDTs on the surface. And then for the data loggers themselves, like I said, we had to get a little bit creative, and we came up with this solar panel system to run our Campbell scientific data logger. This was a little bit interesting. We had to become some electrical engineers for a little while to understand, okay, how do we actually maintain power? We went with deep cycle batteries and monitored the voltage in the batteries. And it was an interesting challenge, and what we ended up having to do is we would cycle the LVDT system, which was independent from the RH and temperature system. The RH and temperature system takes very little to no power, but the LVDTs are quite power hungry. And since we're in Chicago, we have lots of wonderful weather, where even though we have the solar panel, we aren't always generating a lot of electricity. And so that's what necessitated us to have to start cycling these LVDTs. And so then we were able to monitor this over the course of a year. And I know this data looks like a lot of noise, but that is actually the daily cycling. On the left-hand side, that's the relative humidity. And then on the right over here is the temperature. And you can see, so as we get into winter, the average temperature goes down and then back up. So exactly as we'd expect. And then over here with the relative humidity, since we placed the RH and temperature sensors at different depths, as we went deeper through the concrete, you can see that each of these curves start to diverge, which is also what we would expect. We get drying at the top of the slab, and the interior of the concrete stays at a higher RH for much, much longer. This RH difference is not extreme in the first year. We're at maybe a minimum here of about 86% relative humidity, where the interior is still at about 98, so right around 10% RH difference. For the joint opening and lift-off sensors, we did actually start to measure some of these changes. And you can also see that this movement is the same as this type of data, where we get some daily cycling in the temperature, and so we get daily cycling in that slab movement. That's actually not noise. So we got pretty decent agreement between our liftoff sensors. The green one and the purple one are showing vertical movement, so it cycles every day. But the external ones actually showed movement down. Actually, this confounded us. This was an interesting result. But when we later did the modeling, where we started to plug in this data, we found that we weren't actually getting curling upward in the corners. We were actually getting curling downwards, which was unexpected, but then it was reinforced by our external measurements. I've just mentioned the modeling, but the modeling is shown here. So the green line is our actual measurements, and it looks like it's much higher, but we actually just offset the data so we could actually see it. And so with the model, by plugging in our RH and temperature data, we were able to model the theoretical lift-off and movement of the slabs. And so the bottom one is from a completely unbound slab, so if it completely debonds from the asphalt underneath, where if we bind the slab to the base, that's where we get the blue line. And if we remove that offset, what happens is this green data will fall right in between the unbound and bound models, which is kind of interesting because they had applied release agent to the asphalt so that the concrete would not bind to the asphalt, but we still got some bonding between the two. We were given more opportunities, and so we said, well, now that we have some experience, let's do this again. This time they gave us a gate. They came to us and said, we have a lot of recycled crushed concrete, what can we do with it? And we said, hey, we'll figure something out for you. And so we wanted to start making pavements with crushed concrete, and so that's what we came up with. And so they first gave us this gate where the two yellow lanes are the lanes that we were allowed to pour and instrument. The one lane was the recycled concrete, and then the other was just their normal paving mix. And so then we could have side-by-side comparisons where we're looking at the internal environment data plus the movement of the slab. Then we were also, to verify some of the results from up here, then we were also given this lane. This is a satellite fuel station. A little bit different set of loading. It's a little bit thinner slab, and we'll look at some of these results. This was much nicer. This one we actually had a wall that we could plug into the power, so we actually used a lot more instruments and we didn't have to worry about power conservation anymore. It was really nice. At the gate, here is the liftoff data for the sensors at the gate. We had a little bit more movement where previously the movement was like 0.003 at a maximum. At the gate we had 0.02. So there was definitely a difference. The pavements are constructed in the same manner. But once it got up to that level, there was very little variation. This makes sense. The pavements are all doweled together, so they act together. So the movement wasn't as great. But over here with the fuel station, we got a lot more movement. And again, looking at the surrounding environment, this was not doweled. This was onto the edge where they just had a curb. And so we got a lot more movement initially. And then all of a sudden, around November, the movement started going nuts. Well, what happened here was this was then placed into service around that time. So we could actually start measuring the deflections caused by, you can see the fuel trucks that are sitting here. And so those are very, very high loadings. And what happened is with the fuel trucks, they started coming and loading our slabs back and forth, and that kind of dislodged things. And so for the rest of the year, we actually measured a lot higher movement because this is an unrestrained pavement, and then it also has all this extra loading. The last project was what I would call short-term, long-term testing. They came to us with an issue where the FAA requires either a thickened edge slab or a reinforced edge slab when at isolation joints. So when, say, a runway is meeting one of the taxiway tie-ins, the runway needs to be able to move independently of the taxiway tie-in, and so you don't get the load transfer between those slabs, so you have to put in an isolation joint. And you need to make this isolation joint carry the entire load, so you either go with the thickened edge or reinforced. No one had actually done studies, though, to verify that, well, these are equivalent design methods. You can imagine a contractor cringes when they see they have to construct that versus just putting a couple of rebars in it. So we said, well, we'll measure, see what the stresses are, see if we're going to get damage. So this was a very different set of instruments that we used. We moved to concrete embedment strain gauges and then also foil gauges that were placed on our reinforcement. And so this was, like I said, short term. So this is overnight. They allowed us to park our research trailer out on the side of a runway where we hooked up and measured as, in this case, it was freight aircraft rolled over our joint. And so we stayed there all night gathering data. With our embedment gauges, we'd mount one at the top and one at the bottom, so that way, hopefully, we'd get the bending behavior in the slab, and so the measurements should be equal and opposite, and that's what we found, which we were like doing cartwheels down the side of the runway. We were so excited, we were freezing and sat there all night when we started getting this data. And so again, we used this data, started feeding it into analytical models to see, well, does this agree? Do our analytical models actually make sense? And they did. So just looking at this first aircraft, the A300, we measured a little over 7 microstrain, and the models showed that we should have gotten exactly 7. So we were actually really close, really, really low strains, and we had very decent agreement. From that, we were able to calculate peak stresses in our slabs, because that's what O'Hare was really worried about, is were we going to exceed the tensile capacity of our concrete and get a bunch of premature cracking. And so we were able to tell them all of our stresses are going to be quite low, under 600 psi. Concrete should handle that fine. They also went back with us and did some HWD testing, and with that they actually showed a little bit lower stresses than what our models and what our instruments said. And so we're still trying to reconcile that. We're also expanding it to the rest of the aircraft. We love field testing. We get a lot of data, a lot of really interesting data. We used it both in the short term and long term, short term. But the key is always communication. With O'Hare, obviously, anybody can't just drive up there and start putting in sensors, so that was always fun coordinating with the designers and the contractors and everybody involved. Again, all of the support came from the O'Hare Modernization Program. Daniel Castaneda and Yishi Liu were the other grad students that were heavily involved, as well as Armin Armakanian, who's the co-author.